Far beyond the Milky Way, beyond the galaxies bright enough to be seen through ordinary telescopes, there is a region of cosmic history that reaches us only as a faint infrared glow. The light arriving from there began its journey more than 13 billion years ago. It left its sources when the universe was still young, before familiar spiral galaxies had formed, before the sun existed, and before most of the elements now found on Earth had been created. For generations, astronomers could approach this early era only indirectly. They could measure the afterglow of the Big Bang. They could study slightly later galaxies and calculate backward. They could build computer models in which gravity gathered thin clouds of hydrogen and helium into the first stars, then slowly assembled those stars into the earliest galaxies. The broad outline seemed reasonable. Small structures should appear first. Larger systems should take longer. Galaxy formation was expected to begin as a gradual process, limited by the time required for gas to cool, stars to ignite, and gravity to draw scattered material together. Then, the James Webb Space Telescope began to look. Webb was built to receive infrared light, including wavelengths stretched by the expansion of the universe during their long passage toward us. Its instruments can separate faint objects from the surrounding sky and divide their light into spectra, allowing astronomers to estimate distances, identify chemical signatures, and study stars and gas in galaxies that existed only a few 100 million years after the Big Bang. NASA's science. When the first deep observations arrived, the young universe did not appear empty or hesitant. It appeared busy. Astronomers found distant galaxy candidates in greater numbers than many early predictions had suggested. Some seemed unexpectedly luminous. Some appeared to contain enough stars that their growth must have begun very early. Spectroscopic measurements confirm luminous galaxies seen roughly 300 million years after the Big Bang, demonstrating that substantial star-forming systems were already present at an age when the universe was only a small fraction of its current lifetime. This did not mean that modern cosmology had suddenly failed. Science rarely changes in one clean motion. A surprising observation may reveal a problem in the data, an assumption in a model, or a piece of physics that had been treated too simply. The brightness of an early galaxy does not translate directly into its mass. Young stars can produce great amounts of ultraviolet light. Dust can hide some wavelengths and reshape others. Growing black holes may add their own glow. Distance estimates based on images must be tested through spectroscopy before they become secure. So Webb's early results did not replace the old story with a finished new one. They opened the story. The question was no longer only when the first galaxies appeared. It became how they were able to gather gas, form stars, build structure, and sometimes grow bright so soon. It became a question of whether star formation in the early universe was more efficient than expected, whether brief bursts of activity made young galaxies appear unusually luminous, and whether early black holes contributed more light than astronomers had assumed. Webb has also found signs that some early galaxies were already interacting with the neutral hydrogen surrounding them. One distant system, observed as it existed about 330 million years after the Big Bang, showed evidence that energetic radiation was beginning to affect the cosmic fog around it, offering a glimpse of the long transformation known as reionization. That transformation did not happen everywhere at once. The first galaxies emerged inside a universe still filled with cold gas, each one illuminating only a limited region around itself. Across immense stretches of time, those regions expanded and joined, gradually making the universe transparent to ultraviolet light. Tonight, the journey begins inside that unfinished dawn, not with a single galaxy that answers every question, but with many faint signals crossing deep time. Some will become secure measurements, some will be revised. A few may disappear when better observations arrive. Together, they are changing the pace of the earliest chapters of cosmic history. And through Webb's mirrors, the young universe is beginning to look less like an empty beginning and more like a place already learning how to shine. To understand why Webb's early galaxies have drawn so much attention, it helps to return to a time before any galaxy existed at all. The universe had already passed through its first great transformation. In its earliest moments, matter and radiation were packed together in a hot, expanding state. Protons, electrons, and light moved through a dense plasma, continually interacting. Photons could not travel freely for long before colliding with charged particles. There were no transparent skies, no stars, and no clear paths through space. As expansion continued, the universe cooled. About 380,000 years after the Big Bang, electrons joined with atomic nuclei to form neutral atoms, mostly hydrogen, with smaller amounts of helium. Light was finally able to move through space without being repeatedly scattered. That released the ancient radiation now observed as the cosmic microwave background. It is the oldest light astronomers can detect directly. Across the sky, it appears nearly uniform, but not perfectly so. Tiny variations in temperature reveal that matter was distributed with slight differences in density. Some regions contained a little more material than others. The contrast was very small, yet gravity had something to work with. Those small variations became the beginnings of everything that followed. After the cosmic microwave background was released, the universe entered an era often called the Cosmic Dark Ages. The name does not mean that nothing happened. Matter continued to move, gravity continued to act, space continued to expand. But no stars had yet formed to fill the universe with new light. Hydrogen and helium gathered inside growing concentrations of dark matter. Dark matter does not emit light, and its exact nature remains unknown. Its gravitational influence, however, can be measured throughout the universe. Long before ordinary matter formed stars, dark matter had begun collecting into extended structures known as halos. These halos became gravitational wells into which gas could fall. A halo alone was not a galaxy. Gas had to enter it, lose energy, become denser, and cool enough for gravity to compress it further. In the early universe, this was difficult because the first gas contained almost none of the heavier elements that later generations of stars would create. Carbon, oxygen, silicon, iron, and the many atoms that now help interstellar clouds radiate heat had not yet been made in meaningful amounts. The first stars formed from simpler material. Hydrogen gathered into dense pockets. As a cloud contracted, gravitational energy became heat. If the center grew dense and hot enough, nuclear fusion began. The first stellar light entered the universe. Astronomers have not yet obtained an uncontested direct image of a single first-generation star. These earliest objects, often called population 3 stars, are predicted from models of cosmic evolution and from the chemical record left in later stars. They may have differed from most stars that exist today. Without heavy elements to help their parent clouds cool and fragment, some early clouds may have collapsed into unusually massive stars. Such stars would have lived briefly by cosmic standards. Their cores would have burned through nuclear fuel rapidly, and some may have ended as powerful supernovae or collapsed into black holes. The details remain uncertain. The earliest stellar populations may have included a wider range of masses than older models assumed. Their formation may have varied from one environment to another. Their light may have mixed with radiation from young black holes, dense star clusters, and rapidly changing clouds of gas. This uncertainty matters because the first galaxies were built from these first sources of light. A young galaxy was not a smaller version of the Milky Way. It had no settled spiral disk, no long history of repeated stellar generations, and no broad supply of heavy elements accumulated over billions of years. It was a changing concentration of gas, dark matter, stars, radiation, and perhaps black holes, shaped by rapid inflow and frequent interaction. Small systems approached one another. Some passed nearby and disturbed the gas within each other. Others merged. Fresh material moved inward along the growing structure of the cosmic web. Star formation could begin in one region, fade, and then rise again after another supply of gas arrived. This was the process astronomers expected Webb to observe. Before its launch, computer simulations offered many possible versions of cosmic dawn. In most of them, small dark matter halos appeared first, followed by early star-forming systems. These systems gradually merged into larger galaxies. Over time, stars enriched the surrounding gas with heavier elements, making later clouds better able to cool and form new generations of stars. The uncertainty lay in the rate. How quickly could gas settle into the earliest halos? How efficiently could it become stars? How much light would those stars produce? How often would young galaxies brighten in short bursts, rather than remain steadily active? These questions are linked, but they are not identical. A galaxy can appear bright without containing an enormous mass of stars. A compact population of hot, young stars may emit intense ultraviolet radiation. A brief episode of rapid star formation can temporarily make a modest galaxy look far more prominent than it will appear a few million years later. This is one reason early Webb images required careful interpretation. A deep image records brightness through selected wavelength filters. From the pattern of light across those filters, astronomers can estimate whether a galaxy lies nearby or far away. Very distant galaxies can appear to vanish in filters that correspond to wavelengths absorbed by neutral hydrogen, while remaining visible at longer wavelengths. This method is powerful, but it provides an estimate rather than a final distance. A nearer object containing dust, strong emission lines, or an unusual stellar population can sometimes resemble a more distant galaxy. Spectroscopy offers a more secure. It spreads the incoming light into its component wavelengths and can reveal features shifted by cosmic expansion. The amount of that shift is called redshift. As the universe expands, the wavelength of traveling light is stretched. Radiation that left a young galaxy in ultraviolet wavelengths may arrive at Webb in the infrared. Greater redshift usually means the light has traveled from an earlier cosmic time, though translating redshift into an exact age depends on the cosmological model used. Webb was designed for this work. Its large segmented mirror gathers faint radiation. Its instruments operate at infrared wavelengths. The telescope remains cold behind a layered sunshield, reducing the heat that might otherwise overwhelm weak signals from distant space. These engineering choices turn cosmic expansion from an obstacle into a guide. The universe has carried early starlight into the part of the spectrum where Webb can receive it. Yet receiving the light is only the first step. Astronomers must determine what produced it. Young stars are one possibility. Accreting black holes are another. Strong emission from ionized gas may increase the brightness measured in a particular filter. Dust can absorb some wavelengths and release energy at others. Even the shape of a galaxy can be difficult to judge. A faint object may occupy only a few image pixels. What looks like one compact system may contain several smaller regions. Gravitational lensing by foreground matter can magnify a galaxy while also stretching or duplicating its image. The telescope records the light faithfully, but the universe has already altered that light during its passage. This is why the story of the first galaxies cannot be rewritten by brightness alone. Each object must be tested. Distances become firmer through spectroscopy. Stellar masses depend on models of star formation, age, dust, and chemical composition. Black hole activity must be separated from starlight. Lensing magnification must be calculated. Samples must grow large enough to show whether a surprising object is common or rare. The early universe did not leave behind a simple photograph. It sent layered evidence, and as Webb begins to separate those layers, the first galaxies are becoming visible, not as finished islands of stars, but as changing structures inside a universe still learning how to become transparent. The first deep images from Webb did not arrive as a neatly ordered history of the young universe. They arrived as fields of light. Thousands of galaxies appeared across small patches of sky, some nearby in cosmic terms, others so distant that their visible light had been stretched beyond the range of human eyes. Each object occupied its own place in time. A single image contained galaxies separated not only by distance, but by billions of years of evolution. Among them were a few faint sources that seemed to come from an age earlier than any galaxy securely observed before. At first, these sources were identified through color. Webb's near-infrared camera records the sky through several filters, each admitting a different band of wavelengths. A distant galaxy may appear in the longer wavelength filters while disappearing from shorter ones. This sudden change occurs because neutral hydrogen absorbs ultraviolet radiation below a particular wavelength. As cosmic expansion stretches the light, the location of that break shifts farther into the infrared. By measuring where a galaxy appears and where it vanishes, astronomers can estimate its redshift. The method allows researchers to search enormous image fields for objects that may belong to the first few 100 million years of cosmic history. It also creates uncertainty. A dusty galaxy at a later time can sometimes imitate the colors of a much earlier object. A nearby source with strong emission lines may brighten one filter enough to resemble a high redshift galaxy. Detector noise overlapping objects and the limited number of photons can all influence the result. For this reason, the earliest Webb candidates were invitations to look again. Spectroscopy would decide which ones truly belong to cosmic dawn. One of the most important observing programs carrying out this work is the James Webb Space Telescope Advanced Deep Extragalactic Survey, known as JADES. It uses long exposures with Webb's cameras and spectrographs in regions of sky already studied by earlier observatories. These fields were chosen carefully. They contain relatively little foreground dust from the Milky Way. Decades of observations from Hubble, Chandra, Spitzer, and ground-based telescopes provide layers of supporting information. Webb can look into these familiar areas with new sensitivity, adding infrared detail to a record that astronomers have been building for years. The result is not simply a deeper picture, it is a more complete history of the light crossing that picture. In one JADES field, researchers found a source later named JWST 14-0. Its colors suggested a very great distance. To test that estimate, Webb's near-infrared spectrograph observed it for almost 10 hours. The spectrum showed a redshift of about 14.3. The galaxy was seen as it existed less than 300 million years after the Big Bang. For a human lifetime, 300 million years sounds almost without limit. Against the age of the universe, it is an opening interval. The cosmos was then only about 2% of its present age. The light-reaching Webb had traveled through nearly all subsequent cosmic history. It crossed the era when galaxies developed mature shapes. It continued while generations of stars created carbon, oxygen, and iron. It moved through space as the Milky Way assembled, as the Sun formed, and as planets gathered from a disk around it. By the time that light entered Webb's mirror, its source had almost certainly changed beyond recognition. What the telescope received was not the galaxy as it is now. It was the galaxy as it had once been. JWST 14-0 was notable not only for its distance, it was also brighter and larger than many astronomers expected a galaxy from such an early time to be. Its luminous region extended across more than a compact point, suggesting that much of its light came from stars distributed through the galaxy, rather than from a single unresolved black hole. The galaxy also showed evidence of material already altered by stellar activity. Observations at longer infrared wavelengths indicated strong emission associated with ionized oxygen. Oxygen did not emerge directly from the Big Bang. It had to be produced inside stars and released into surrounding gas. This meant that stars had formed, lived, and returned processed material to the galaxy before the moment Webb was observing. The available time was limited. The galaxy's earliest stellar generations must have appeared sooner still. This does not require stars and galaxies to have formed instantly. It does suggest that once suitable dark matter halos and gas clouds were in place, growth could proceed rapidly. Star formation may have been vigorous, gas may have flowed into young systems efficiently. Stellar populations may have produced more ultraviolet light for a given amount of mass than many earlier models assumed. JWST 14-0 was not alone. Other spectroscopically confirmed galaxies have been found at similarly early times. As observing programs expanded, the record boundary moved closer to the Big Bang. A galaxy known as MZ414 was confirmed at a slightly higher redshift, corresponding to a time around 280 million years after the universe began. The difference between these objects is only a small interval on a cosmic calendar. Scientifically, Each additional step matters. At such early times, a shift of a few tens of millions of years represents a meaningful fraction of the period available for the first structures to develop. A galaxy observed 280 million years after the Big Bang had less time to gather matter, form stars, enrich its gas, and become visible than one observed several hundred million years later. Yet the existence of one bright early galaxy does not reveal the average condition of the universe. The brightest sources are the easiest to find. They may represent rare environments where matter accumulated earlier than usual. They may have been caught during temporary bursts of star formation. Their light may have been amplified by conditions that did not apply to most galaxies of the same age. A telescope begins with what can be detected. Only later, through larger samples, does it approach what was typical. This distinction has softened some of the earliest claims that Webb had found galaxies too massive to exist within the standard cosmological picture. Initial mass estimates were often based on limited imaging. When spectroscopy and improved models were added, some candidates moved to lower redshifts. Others proved less massive than first thought. Young stars can be intensely luminous. Gas surrounding them can emit strongly at particular wavelengths. A growing black hole can contribute light that was initially attributed to stars. When these effects are separated, the inferred stellar mass may decline, even though the observed brightness remains unchanged. The early universe has not become impossible. It has become more active and more varied. Before Webb, many models produced fewer bright galaxies at very high redshift than observations now suggest. Researchers are therefore adjusting the details of how early galaxies convert gas into stars, how often their activity occurs in bursts, how stellar feedback regulates their growth, and how their light should be interpreted. Feedback is central to the problem. Massive stars release ultraviolet radiation. Stellar winds push into surrounding gas. Supernova explosions inject energy and newly formed elements into the galaxy. These processes can disperse star-forming clouds and temporarily slow further growth. They can also compress nearby gas and help create new dense regions. In a small early galaxy, the balance may change rapidly. A period of star formation could brighten the system for several million years. Explosions might then clear gas from its center, reducing activity. Fresh material flowing in from the cosmic web could begin another episode later. Seen across human timescales, the galaxy appears fixed. Across its own history, it may be pulsing through cycles of growth and interruption. Webb captures only one part of that motion. The photons entering its instruments preserve the state of a galaxy during a narrow interval long ago. Astronomers must use that frozen signal to infer what came before and what followed. This is why surveys need many galaxies. One object may reveal what was possible. A population reveals how often it happened. As Webb studies wider fields and returns to the deepest ones, the list of confirmed early galaxies continues to grow. Their spectra provide more than distances. They show emission from hydrogen and oxygen. They reveal the effects of hot young stars. They sometimes expose material moving outward or radiation escaping into intergalactic space. Each spectrum is sparse compared with the rich detail available from nearby galaxies. Yet every line carries a physical history. A feature produced by oxygen means earlier stars existed. A strong hydrogen line can reveal active star formations or an opening through the surrounding gas. The shape of the ultraviolet continuum offers clues about dust, stellar age, and chemical composition. The galaxies remain faint points and small smudges on the detector. Behind those shapes are the first working systems of cosmic evolution. Gas is entering. Stars are forming. Elements are accumulating. Radiation is beginning to change the space between galaxies. Webb has not found a single moment when galaxies suddenly appeared. It is uncovering a period in which many processes began at different rates in different places, inside structures that could brighten, merge, fade, and grow. The old picture was not wrong to begin with small seeds. What has changed is the speed and diversity of what those seeds could become. Near the edge of Webb's vision, the first galaxies are no longer distant placeholders in a model. They are becoming individual places. each carrying its own early version of the universe. Beneath the growing census of early galaxies, another complication has begun to appear. Some of the light Webb detects may not come from stars alone. At first glance, a distant galaxy can seem like a simple object. Its image may occupy only a small cluster of pixels, surrounded by empty sky. Yet within that compact glow, several sources of radiation can overlap. Young stars illuminate clouds of gas. Heated dust releases infrared energy. Supernova remnants disturb the surrounding material, and near the center, matter may be falling toward a black hole. The telescope receives all of this together. Separating it changes the story of how quickly the first galaxies grew. Before Webb, astronomers knew that supermassive black holes existed surprisingly early. Bright quasars had already been observed when the universe was less than 1 billion years old. Some contained black holes with masses equivalent to hundreds of millions or even billions of suns. Their existence created a timing problem. A black hole does not begin at that scale. It must grow from a smaller seed by consuming gas, merging with other black holes, or both. The rate cannot increase without limit. As matter falls inward, it becomes hot and luminous. The radiation it produces pushes outward against the incoming material, sometimes slowing the flow that feeds the black hole. Growing from the remnant of an ordinary massive star to 1 billion solar masses in only several 100 million years is possible under favorable conditions. But difficult, the seed would need to form early, remain well supplied with gas, and spend much of its time growing rapidly. Another path begins with a larger seed. A dense primordial gas cloud may, under certain conditions, collapse almost directly into a black hole. This could produce an object thousands or tens of thousands of times more massive than the Sun at birth. Dense star clusters may offer another route, allowing repeated collisions and mergers to create a heavier starting point. Astronomers do not yet know which pathway dominated. Webb is beginning to observe the population that may connect those first seeds with the later quasars. Among its most puzzling discoveries are small, compact sources that appear red in infrared images. Researchers often refer to them as little red dots. The name describes their appearance rather than their nature. They are unresolved or barely resolved, suggesting that much of their light comes from a region far smaller than a mature galaxy. Many existed during the first 1 or 2 billion years of cosmic history. Some spectra contain broad hydrogen emission lines, a feature commonly associated with gas moving at high speed near an actively feeding black hole. At the same time, their light can also resemble that of dense stellar populations. This has made them difficult to classify. One interpretation places a growing black hole at the center, hidden within gas and dust. Material orbiting near the black hole moves rapidly and becomes intensely hot. Dust surrounding the region absorbs shorter wavelength radiation and re-emits energy in the infrared, giving the source its red appearance. Another interpretation gives more of the light to stars. A compact galaxy undergoing a concentrated burst of star formation may contain enough hot stars, glowing gas and dust to imitate some features of an active black hole. In certain models, the source may be both at once, a young galaxy forming stars around a rapidly growing central object. That possibility is especially important. Galaxies and their central black holes appear closely connected in the later universe. In many nearby systems, the mass of the central black hole correlates with properties of the surrounding galaxy. This relationship suggests some form of shared growth. Although the exact mechanisms remain under study, the early universe allows astronomers to ask which came first. Did galaxies build dense central regions that later fed black holes? Did large black hole seeds form first and influence the growth of the galaxies around them? Or did both develop together, each changing the environment of the other? Webb has found examples that may favor more than one route. Some compact, early sources appear to contain black holes unusually massive compared with the stars surrounding them. In the nearby universe, a central represents only a small fraction of its galaxy's stellar mass. In certain distant systems, the inferred black hole may account for a much larger share. This could mean that the black hole grew ahead of the galaxy. It could also mean that the stellar mass has been underestimated, or that the black hole's mass has been overestimated because the motions of its gas are more complicated than the models assume. At such distances, every conclusion rests on layers of interpretation. A broad spectral line can indicate rapidly orbiting gas, but winds flowing away from the center may also broaden it. Dust geometry changes which regions are visible. A compact cluster of stars can remain unresolved. Gravitational lensing may magnify some parts of a source more strongly than others. The observations are real. The physical picture must be assembled carefully around them. One early object studied with Webb contains an actively growing black hole in a galaxy, seen roughly 570 million years after the Big Bang. Its light belongs to the little red dot population, placing it near the beginning of the era in which such compact sources are commonly detected. The black hole appears to be feeding rapidly. Its surrounding galaxy remains small. This is not yet proof that black holes generally formed before galaxies. It is one example from a young and unusual population. But it demonstrates that strong black hole growth was already underway while some galaxies were still assembling much of their stellar structure. The boundary between galaxy light and black hole light therefore becomes central to the question of early brightness. Imagine a distant source whose total radiation is initially attributed to stars. Astronomers estimate the age and brightness of those stars, then infer how much stellar mass must be present. If part of the glow actually comes from gas falling into a black hole, the stellar contribution is smaller. The galaxy may then contain less stellar mass than first calculated. An object that seemed too massive for its age may become easier to explain. This adjustment has already influenced the interpretation of several early Webb sources. Some of the first claims of unexpectedly massive galaxies weakened when researchers included more flexible star formation histories, strong emission lines, different dust properties, or possible active galactic nuclei. Yet black holes do not explain everything. Many early galaxies show light spread across regions too broad to come from a single central source. Their spectra can be dominated by stars and ionized gas rather than by clear signs of accretion. The abundance of bright galaxies remains an active problem, even after likely black hole contributions are considered. The new story is not that Webb mistook black holes for galaxies. It is that the early universe contained more overlapping forms of activity than simple models captured. Stars and black holes were growing in the same limited reservoirs of gas. Their effects could oppose each other. A feeding black hole releases radiation and may launch winds that drive material away from the center. If those outflows remove or heat enough gas, star formation can decline. This process is often called active galactic nucleus feedback. But an outflow can also compress gas along its edges. Under some conditions, the pressure may help dense clouds collapse and form stars. The result depends on the energy of the outflow, the structure of the galaxy, the amount of available gas, and the depth of the surrounding gravitational well. In small early systems, the balance may shift quickly. A black hole could brighten for a time, disturb its host, then become faint when its fuel supply changes. The galaxy could continue gathering new material from outside. Star formation might return in another region. A later merger could drive gas toward the center again. What Webb observes is one frame from this longer exchange. A little red dot may represent a brief stage rather than a permanent class galaxy. This may help explain why similar objects appear common during one interval of cosmic history and much rarer later. They could be an early phase in which dense gas, Young's dust, and black hole growth remain packed into a small volume before the system expands or clears. Their compactedness is part of the clue. In a mature spiral galaxy, stars may extend across tens of thousands of light years. A central active region occupies only a small fraction of that space. In some early systems, much of the visible galaxy may fit inside a region that would seem small beside the Milky Way's central bulge. Gas densities could be high. Star formation could be concentrated. A central black hole would not be separated from the wider galaxy by the spacious structure seen today. everything would be occurring close together. There is a generational thread hidden inside the observations. The iron in human blood, the oxygen drawn into the lungs, and the carbon carried through every living cell were made through stellar processes that had barely begun when these objects shone. The first black holes were also gathering matter, shaping their surroundings, and sending energy into galaxies that contained only an early trace of the elements now familiar on Earth. No observer was present. There were no planets beneath those skies that science can presently identify, and no settled constellations from which to view them. The only record was radiation leaving the young galaxies and continuing outward. That radiation traveled while later generations of stars formed. It passed through an evolving universe as heavier elements accumulated. Planetary systems emerged, and one small world eventually developed instruments capable of receiving the signal. Webb does not see the beginning directly. It sees evidence that survived the distance. A broad hydrogen line, a compact red source, an infrared excess, a galaxy whose center may contain a black hole growing faster than the stars around it. Each piece narrows the range of possible histories. As more spectra are collected, some little red dots will likely separate into different groups. Some prove dominated by active black holes. Others may be dense stellar systems. A number may contain both in proportions that change with time. Their ambiguity is not a weakness in the observation. It is a sign that the categories developed from nearby galaxies do not always transfer cleanly into the first billion years. The early universe was not populated by finished versions of modern objects. Its galaxies were assembling their identities. A source could be a star-forming galaxy, a black hole host, a dust-covered nucleus, and a temporary burst of activity at the same moment. The names astronomers use divide these processes so they can be studied. Nature had no need to keep them separate. This is one of the deeper revisions Webb is bringing to the history of galaxies. The question is no longer only how quickly stars accumulated. It is how stars, gas, dust, gravity, and black holes shared the same young structures, each influencing the rate at which the others could grow. Far inside those compact points of infrared light, the first galaxies may already have been negotiating the relationship that would shape them for billions of years. Beyond the first stars and growing black holes, another transformation was spreading through the young universe. It did not begin in one place. There was no single flash that suddenly cleared the cosmos. Instead, light emerged inside many small regions, each surrounding a young galaxy, each expanding into the neutral hydrogen that filled the space between them. This long transition is known as cosmic reionization. The name describes a change in the condition of hydrogen. After the universe cooled enough for electrons to join atomic nuclei, most hydrogen became neutral. For hundreds of millions of years, this gas occupied intergalactic space. It did not block every form of radiation, but it strongly absorbed ultraviolet light, energetic enough to remove electrons from hydrogen atoms. When the first luminous objects appeared, they began sending out that kind of radiation. A sufficiently energetic photon could strike a neutral hydrogen atom and separate its electron from its proton. The atom became ionized. One event affected almost nothing on a cosmic scale, but stars produce immense numbers of photons. Galaxies containing many hot young stars could create expanding regions of ionized gas around themselves. Astronomers often describe these regions as bubbles. The word is useful, though the real structures were uneven. Gas was distributed along filaments and gathered around dark matter halos. Some directions contained dense material that absorbed radiation quickly. Other paths were more open. The ionized regions stretched, narrowed, overlapped, and changed as galaxy brightened or faded. At first, each galaxy occupied a small clearing in a mostly neutral universe while its time. Over time, neighboring clearings reached one another. The spaces between galaxies from predominantly neutral to predominantly ionized. By roughly 1 billion years after the Big Bang, most intergalactic hydrogen had entered the ionized state that remains common today. The broad outcome is well established. The details are not. Astronomers still want to know which objects supplied most of the radiation. They want to understand how efficiently that radiation escaped from galaxies, how quickly ionized regions grew, and why some areas became transparent earlier than others. Webb was designed to study the galaxies living inside this transition. It cannot simply photograph reionization as a glowing boundary moving across space. Much of the hydrogen involved is too diffuse to appear in an ordinary image. Instead, Webb studies the sources whose radiation may have driven the change, along with the traces left in their spectra. One of the most useful traces comes from hydrogen itself. When an electron inside a hydrogen atom changes energy levels, the atom can emit light at specific wavelengths. A strong ultraviolet feature known as Lyman alpha is especially important in studies of young galaxies. Inside a galaxy, hot stars ionize nearby hydrogen. When electrons later recombine with protons, the surrounding gas can produce Lyman alpha photons. Those photons begin moving outward, but their journey is difficult. Neutral hydrogen absorbs and scatters Lyman alpha light with great efficiency. A photon may encounter hydrogen inside its own galaxy, in material flowing around the galaxy, or in the intergalactic medium beyond it. Instead of traveling directly toward a telescope, it may be redirected many times. Dust may absorb it. Cosmic expansion may shift its wavelength enough to help it pass through some regions. Whether Webb detects this light depends not only on the galaxy producing it, but also on the environment surrounding the galaxy. A strong Lyman alpha signal from a very early source may suggest that the galaxy sits in an ionized region large enough for some photons to escape before encountering neutral gas. This turns the galaxy into more than a distant object. It becomes a probe of the space around it. Some early galaxies observed by Webb appear to exist in groups. Their positions suggest that several young systems were forming within the same large concentration of matter. If each one released ionizing radiation, their combined effect could create a bubble larger than any one galaxy could maintain alone. This cooperative picture may help explain how faint galaxies contributed to reionization. The brightest early galaxies receive the most attention because they are easier to detect and study. Yet they were likely outnumbered by smaller systems. A single faint galaxy may have released a modest amount of ionizing radiation. An enormous population of such galaxies could still have provided much of the total. The difficulty lies in counting objects that remain below even Webb's sensitivity. Astronomers observe the brighter part of the population and use models to estimate how many fainter galaxies existed. Small changes in that extrapolation can produce large differences in the total amount of radiation. Another uncertainty concerns escape. A galaxy may create many ionizing photons, but that does not mean those photons reach intergalactic space. Dense gas and dust can absorb them before they leave. The fraction that escapes depends on the structure of the galaxy. Young systems may have been irregular. Star formation could occur in compact clusters. Supernovae and stellar winds might open channels through the surrounding gas. Radiation could pass outward along those paths, while remaining trapped in other directions. The escape fraction may therefore change over time. During one stage, a galaxy could be wrapped in dense material and contribute little to reionization beyond its immediate surroundings. After massive stars and supernovae disturbed that gas, radiation might begin leaking through newly cleared regions. Later inflows could close some paths again. Webb observes these galaxies at single moments within that cycle. A spectrum may reveal strong emission from highly ionized gas, indicating an intense radiation field. The shape of the ultraviolet light may suggest a young, metal-poor stellar population. Certain combinations of spectral lines can help astronomers estimate whether the stars were unusually hot or whether a central black hole contributed additional energy. None of these measurements alone provides a complete answer. Together, they begin to define the kinds of sources present during reionization. The earliest stars formed from gas containing almost no elements heavier than helium. Their light may have been harder, meaning it contained a greater share of high-energy photons. As generations of stars formed and died, they added heavier elements to the surrounding gas. Those elements changed how clouds cooled, how stars formed, and what kinds of radiation stellar populations produced. Reionization was therefore linked to chemical evolution. It was not simply a curtain of hydrogen being pulled aside. Galaxies were changing internally while they changed the space around them. Their stars manufactured new elements. Their supernovae distributed those elements. Their winds shaped channels through gas. Their black holes may have added radiation of their own. Their mergers brought new fuel and disturbed existing structures. A galaxy's contribution to reionization depended on this entire history. The process also changed what later galaxies experienced. Before reionization, small dark matter halos could gather cool neutral gas more easily. As ultraviolet radiation spread through intergalactic space, it heated that gas. Warmer gas resisted falling into the smallest halos. Some low-mass systems may have lost access to the material needed for continued star formation. In this way, the first galaxies altered the conditions under which other galaxies could grow. Light became a form of feedback operating across intergalactic distances. A galaxy could ionize and heat gas far beyond the region occupied by its stars. That changed the future of nearby structures, including objects too faint to observe directly. The universe was beginning to regulate its own growth. There is no visible marking where this happened. From Earth, the night sky does not preserve a simple boundary between neutral and ionized time. The evidence is spread across distant galaxy spectra. The absorption patterns of quasars, the polarization of the cosmic microwave background, and the large-scale distribution of hydrogen inferred through radio observations. Each method sees a different part of the transition. Webb contributes the galaxies themselves. It reveals their brightness, their abundance, their chemical state, and the radiation produced by their stars and black holes. It can identify systems whose light appears to pass through unexpectedly transparent regions. It can study concentrations of galaxies that may have formed early ionized bubbles. Other observatories approach the neutral gas more directly. Radio telescopes are being developed to detect the faint signal produced by hydrogen at a wavelength of 21 centimeters. Cosmic expansion stretches this radiation to longer radio wavelengths before it reaches Earth. In principle, maps of that signal could show where neutral hydrogen remained and where ionized bubbles had formed. Such maps would provide the wider landscape around Webb's galaxies. One telescope could reveal the sources. Another could reveal the medium they were changing. Together, they may eventually show reionization, not as a smooth transition, but as a patchwork. Dense regions containing many galaxies likely changed first. More isolated regions may have remained neutral longer. The bubbles grew around clusters of activity, joined along the cosmic web, and left shrinking pockets of neutral hydrogen between them. The universe became transparent unevenly. That unevenness carries information about the first galaxy populations. Large bubbles appearing early would imply strong or numerous ionizing sources. Smaller, delayed regions would suggest weaker escape or fewer galaxies. The shapes of the bubbles could reveal how galaxies were distributed and how radiation moved through the surrounding gas. Webb's observations have made some early galaxies look capable of producing substantial amounts of energetic radiation. Their young stellar populations can be bright in the ultraviolet. Strong emission lines indicate active, highly ionized gas. Some appear to be gathered in environments where several galaxies could combine their influence. But the final accounting remains open. Bright galaxies may contribute more than earlier models assumed. Faint galaxies may still dominate through their numbers. Growing black holes may add radiation in ways that vary from one system to another. The answer may change across time. The sources responsible for the beginning of reionization need not be the same population that completed it. In the earliest phase, rare galaxies or black holes in dense regions may have created isolated bubbles. As more galaxies formed, the combined radiation from common smaller systems could have expanded the ionized volume rapidly. Later, the remaining neutral pockets may have survived in places where gas was dense enough to resist the surrounding radiation. This gradual changing picture suits the evidence better than a single universal cause. Reionization lasted hundreds of millions of years. During that interval, the objects producing light were evolving quickly. From a human perspective, hydrogen changing from neutral to ionized may seem remote and abstract. Yet this transition helped establish the transparent intergalactic environment through which much later starlight would travel. The light of Galaxies crosses ionized space more freely. The long observational history of the cosmos depends, in part, on what those first sources did. There is also a quieter continuity in the hydrogen itself. Hydrogen formed in the early universe. It gathered into the first stars, remained in the spaces between galaxies, and became ionized by radiation from objects that no longer exist in their original form. Much of the hydrogen around and within us belongs to that same cosmic inheritance. Its electrons and protons have joined, separated, and joined again through environments spanning nearly the full age of the universe. Webb now receives light shaped by that history. A missing wavelength can mark absorption by neutral gas. An emission line can reveal a cloud illuminated by young stars. A transparent path may indicate an ionized region extending beyond a galaxy that existed for only a brief period in cosmic time. The telescope does not watch the fog lift. It reconstructs the clearing from the light that managed to pass through. And in those surviving signals, the first galaxies appear not merely as objects forming within the universe, but as agents beginning to transform it. The first galaxies do not challenge cosmology in a single, simple way. They press against a chain of assumptions. A model of the early universe begins with the distribution of matter. From that starting point, gravity builds dark matter halos. Gas falls into those halos. Clouds cool, stars form. Radiation and explosions push back against further collapse. Galaxies merge, lose material, gain material, and change their brightness over time. Every step contains. Some are based on well-tested physics. Others must be approximated because no simulation can follow every atom, every shockwave, every star, and every photon across the full volume of the observable universe. The earliest Webb results have placed the greatest pressure on those approximations. Large-scale cosmological models describe how structure grows from the small density variations present in the early universe. On the broadest scales, this framework remains successful. It explains the cosmic microwave background, the distribution of galaxies, and the way matter clusters over time. Webb has not overturned that foundation. The tension appears farther down the chain, where dark matter halos begin turning gas into visible galaxies. A simulation may predict how many halos of a certain mass should exist at a given time. It must then estimate how much gas enters those halos, how much of that gas becomes stars, how much light those stars produce, and how strongly feedback removes or heats the remaining material. Small changes in these assumptions can produce large changes in the number of bright galaxies. This is one reason the phrase rewriting the story requires care. The universe has not changed. The equations of gravity have not suddenly become unfamiliar. What is changing is the description of how efficiently young galaxies used the material available to them. Before Webb, many models assumed that early star formation was strongly limited by feedback. Massive young stars release radiation, winds, and supernova energy. In small galaxies with shallow gravitational wells, that energy can push gas outward. If enough material escapes, the galaxy's growth slows. This remains physically reasonable. But the strength and timing of the effect may differ from one young system to another. Gas in the early universe was often arriving rapidly. Dense streams could feed a halo from the surrounding cosmic web. If fresh material entered faster than feedback removed it, if star formation might remain active even while winds and explosions disturbed the galaxy. A compact system could convert gas into stars with greater efficiency for a short period. It might then appear brighter than a model based on a smoother, more regulated history would predict. Bursty star formation offers one possible explanation for the abundance of luminous early galaxies. In this picture, a galaxy does not form stars at a steady rate. It brightens during concentrated episodes, then becomes fainter as its most massive stars die. and its gas supply changes, a survey is more likely to detect the bright phase than the quiet interval. This creates an observational bias. The galaxies entering Webb samples may not represent average systems observed at average moments. They may be the ones caught during their most visible stages. A population of modest galaxies could therefore produce more bright detections than a steady model predicts, without requiring every galaxy to contain an unexpectedly large stellar mass. The stars themselves may also have been different in ways that affected brightness. A stellar population is described partly by its initial mass function, which represents the relative numbers of low mass and high mass stars formed together. In the nearby universe, this distribution has been measured in many environments and often shows broadly similar patterns. The first galaxies formed under different conditions. Their gas contained fewer heavy elements. Their clouds may have been warmer. Magnetic fields, turbulence, and radiation operated in environments with little chemical enrichment. These differences could shift the masses of newly formed stars. If early galaxies produced a greater share of massive stars, they would emit more ultraviolet light for the same total stellar mass. They would look brighter without requiring more matter. Massive stars would also live briefly. Their radiation and supernovae would alter the galaxy quickly, enriching the gas while making later star formation different from the first. The effect would not continue unchanged for long. This makes the earliest galaxies sensitive, observed shortly after a major burst, could appear luminous and chemically young. Another galaxy with a similar total mass, seen after its brightest stars had died, might fall below the detection limit. Two physically related systems could look very different. Dust adds another layer. In nearby galaxies, dust often absorbs ultraviolet and visible light, then re-emits the energy at longer infrared wavelengths. Early galaxies were expected to contain relatively little dust because the elements needed to form dust grains had only recently begun to appear. Yet dust can develop quickly. Supernovae may produce grains. Material flowing from certain evolved stars can add more, though such stars require time to reach that stage. Dust can also grow inside dense clouds once enough heavy elements exist. Even a small amount can alter the light Webb observes. The effect depends on grain composition, size, temperature, and distribution. Dust arranged in clumps may hide some stars while leaving others exposed. A smooth screen produces a different spectrum from a patchy medium. Models must choose how to represent these conditions. If the dust law assumed for a distant galaxy is inaccurate, estimates of stellar age and mass may shift. A galaxy can appear red because its light has traveled from a great distance. It can also appear red because dust absorbed its shorter wavelengths. Separating those effects is one of the basic tasks of early galaxy analysis. Strong emission lines complicate the colors further. Young stars ionize surrounding gas. That gas emits radiation at particular wavelengths, and some lines can contribute a large share of the light measured through a broad filter. A galaxy may appear unusually bright in one band, not because its entire stellar population is stronger, but because an emission line falls inside that band after being shifted by cosmic expansion. This can distort early estimates based on images alone. Spectroscopy helps isolate the line from the underlying starlight. Once that happens, the inferred mass may decrease. A similar revision occurs when a black hole contributes part of the light. Each correction removes some pressure from the most extreme interpretations, but not all of it. Even after accounting for emission lines, dust bursts, and active black holes, some observations continue to suggest that bright galaxies were more common than many pre-Webb models expected. The task is now to determine which physical adjustments are sufficient. One possibility is that gas converted into stars more efficiently in certain early halos. Efficiency here does not mean that all gas became stars. It describes the fraction transformed over a given interval. A modest increase, applied across a population of rapidly growing halos, can produce many more luminous galaxies. Another possibility concerns feedback delay. Radiation and stellar winds begin early, but supernovae require massive stars to reach the ends of their lives. For several million years after a burst begins, a young galaxy may form stars before the strongest, explosive feedback arrives. That interval is brief, but cosmic dawn contains many rapidly changing systems. If Webb preferentially detects them during that opening phase, the bright population could be enhanced. The geometry of gas may matter as much as the total energy released. Feedback does not spread evenly through a galaxy. Winds and radiation move through low-density channels more easily than through dense clouds. Energy may escape without removing the gas that is actively forming stars. A simple model that assumes uniform coupling can therefore overestimate how effectively feedback suppresses growth. More detailed simulations attempt to follow these uneven structures. They model gas collapsing into filaments, knots, and disks. They track radiation moving through a changing medium. They allow supernovae to explode in different environments rather than depositing energy into an average cloud. The greater detail often produces more variable galaxies. Star formation rises and falls. Gas leaves in one direction and enters from another. A galaxy that looks disrupted can continue growing. These simulations are computationally demanding. To model the first galaxies accurately, researchers need large volumes because the brightest systems are rare. They also need fine resolution because star formation occurs on scales far smaller than the distance between galaxies. No single simulation can maximize both perfectly. A large model may contain many galaxies, but simplify their internal structure. A smaller, high-resolution model may capture detailed gas behavior while including too few rare objects for reliable statistics. Astronomers compare several approaches. They use hydrodynamic simulations that follow gas directly. They use semi-analytic models that apply simplified physical rules to large dark matter merger histories. They build empirical models connecting observed galaxies to the halos expected from cosmology. Each method has strengths. Each responds differently when Webb adds new constraints. The new observations are therefore reshaping more than one prediction at a time. They affect the galaxy luminosity function, which describes how common galaxies are at different brightnesses. They affect estimates of stellar mass. They influence models of chemical enrichment, black hole growth, and reionization. A change made to improve one result must remain consistent with the others. Increasing star formation efficiency may produce enough bright galaxies, but it also increases the number of ionizing photons. That could alter the predicted timing of reionization. Changing the stellar mass distribution may boost ultraviolet light, but it also changes the rate of supernovae and the production of heavy elements. Reducing feedback allows faster growth, but it may create galaxies that become too massive at later times. The models must evolve as connected systems. This is what makes Webb's influence so useful. It is not merely adding distant objects to a catalogue. It is forcing different areas of early universe physics to agree with the same set of observations. A successful model must explain how many galaxies existed, how bright they were, what their spectra contained, how quickly they enriched their gas, how their black holes grew, and how their radiation altered intergalactic hydrogen. The solution may not be one dramatic new mechanism. It may be a combination of smaller revisions. Star formation could be more burst-like. Early stellar populations could produce more ultraviolet radiation. Feedback might escape through channels rather than stopping collapse uniformly. Gas inflow could remain strong. Black holes could add light in some compact sources. Dust and emission lines could shift mass estimates. Together, these changes may turn a sparse predicted universe into the busier one Webb observes. There is also the possibility that some assumptions outside galaxy physics will need closer examination. Researchers continue to test whether the abundance of early halos could differ slightly from standard expectations. They examine the properties of dark matter, the statistics of the initial density field, and the influence of cosmological parameters. These possibilities are scientifically important. They are also held to a higher standard. A proposed change to fundamental cosmology must explain far more than early galaxies. It must remain consistent with the cosmic microwave background, gravitational lensing, galaxy clustering, and many other measurements. For now, the simpler path is to test the uncertain physics of galaxy formation first. That is where the greatest flexibility exists. The dark matter halo is not directly observed as starlight. The conversion from halo to galaxy contains many processes that remain difficult to calculate from first principles. Webb is narrowing that freedom. As larger samples arrive, rare bright objects become part of a distribution. Spectra replace uncertain color estimates. Repeated observations reveal which candidates remain secure. The range of acceptable models becomes smaller. Some explanations that fit the first images may fail when asked to reproduce chemical abundances. Others may create enough bright galaxies, but not enough faint ones. A model that succeeds at one redshift may fail at another. Progress comes through these failures. A simulation is not a miniature universe that must be defended. It is a testable description. When observations disagree, the useful response is to locate the assumption responsible and improve it. That process can seem less dramatic than declaring a crisis. It is also how scientific understanding becomes more precise. Webb's deepest fields are still small compared with the whole sky. Cosmic variance means that one field may contain more or fewer galaxies than the universal average. Dense regions form early and can make a survey look unusually populated. Wider observations help measure this effect. They show whether the first deep fields happen to include rare concentrations of matter, or whether luminous galaxies were common across many regions. Lensing surveys offer another path. Massive foreground galaxy clusters bend light from objects behind them, magnifying sources that would otherwise remain invisible. This allows Webb to study fainter galaxies, though the magnification must be modeled carefully. Blank fields provide cleaner statistics. Lensed fields reach deeper. Spectroscopic surveys supply physical detail. Together, they build a more balanced picture. The story will continue changing as these approaches overlap. Some early galaxies, once considered extremely massive, may move downward in mass. New objects may appear at even earlier times. The bright end of the population may prove highly variable, shaped by brief bursts and active black holes. Fainter systems may emerge as the more representative builders of cosmic structure. The result will likely be less simple than either the pre-Webb expectations or the first headlines. There is a present moment anchor in the way this work unfolds. The telescope is not receiving a completed answer from the distant universe. It is collecting photons one exposure at a time, while teams on Earth compare models, revise measurements, and return to the same fields with better questions. The process is slower than the light itself. A photon may cross more than 13 billion years of expanding space, then spend months inside a scientific discussion before its meaning becomes clearer. Nothing about that delay weakens the observation. It is part of how knowledge is built. The first galaxies are too distant to be visited and too old to be watched through their full evolution. Yet their surviving light is enough to reveal where a model bends, where an assumption fails, and where a more accurate history can begin. Webb is not replacing one finished story with another. It is turning the early universe from a broad outline into a system that must account for individual galaxies, individual spectra, and individual moments of growth. And with every revision, the cosmic dawn becomes less like a distant abstraction and more like a physical era whose details can finally be tested. There is another way to understand what Webb is changing. Instead of asking only how many early galaxies existed, astronomers can ask what those galaxies were made of. A distant point of light may seem almost featureless in an image. Through spectroscopy, it becomes a record of physical conditions. The light can reveal which atoms were present, how strongly gas was ionized, how quickly stars were forming, and whether the system had already passed through several generations of stellar life. This chemical history begins with a universe that was simple. In the first minutes after the Big Bang, most ordinary matter took the form of hydrogen and helium, with a small amount of lithium. The carbon, nitrogen, oxygen, silicon, and iron familiar on Earth did not yet exist in significant quantities. Those elements had to be made inside stars. As a star fuses lighter nuclei into heavier ones, its interior gradually changes. Some elements remain locked inside until the star loses material or reaches the end of its life. Massive stars can release newly formed atoms through winds and supernova explosions. The surrounding gas then carries that material into later clouds, where new stars and perhaps planets can form. Every generation modifies what comes next. In nearby galaxies, this process has been operating for billions of years. The gas has been repeatedly enriched, diluted, recycled, and mixed. In the first galaxies, the cycle had only just begun. This makes every detection of a heavier element important. When Webb finds oxygen in a galaxy seen only a few 100 million years after the Big Bang, the oxygen itself is evidence of an earlier history. At least one previous generation of stars must have formed and processed the original hydrogen and helium. Some of those stars must then have returned enriched material to the galaxy. The galaxy being observed is already a second chapter. The first chapter is hidden inside the atoms. This can happen more quickly than intuition suggests. A very massive star may live only a few million years. It can form, burn through its fuel, and end in a supernova while the universe is still extremely young. If many such stars appear in a compact galaxy, chemical enrichment can begin rapidly. The first supernovae would not spread their elements evenly. Their ejecta would move through a changing environment of dense clouds, open cavities, inflowing gas, and other explosions. Some material might leave the galaxy. Some could remain trapped by gravity. Some might mix into the next generation of star-forming clouds. The result would be uneven. One region could contain newly produced oxygen while another remained closer to the original composition of the universe. Webb does not usually resolve these earliest galaxies into fine internal maps. Their structures are too small and distant, but their combined spectra can still show that enrichment has begun. Certain emission lines reveal ionized oxygen. Others trace carbon, nitrogen, or neon. Hydrogen lines indicate active star formation and help estimate how much ionizing radiation is present. The relative strengths of these features allow astronomers to infer temperature, density, chemical abundance, and the hardness of the radiation field. The word hardness refers to the energy distribution of the light. A population containing very hot stars produces a greater fraction of energetic photons. A feeding black hole can produce an even harder spectrum. Gas responds differently to these sources, leaving distinct patterns in its emission lines. The patterns are rarely simple enough to identify one cause without ambiguity. A metal-poor stellar population may resemble a weak active nucleus in some measurements. Dense gas can alter line ratios. Dust can absorb part of the spectrum. Radiation may escape in some directions and remain trapped in others. Astronomers therefore compare several features at once. They build models of stars and gas, then ask which combination reproduce the observed spectrum. Webb has revealed that some early galaxies contain highly ionized gas and strong emission lines, suggesting intense radiation fields. This may arise from very young stellar populations, low chemical abundance, compact star formation, or black hole activity. Often, more than one factor is involved. These conditions make early galaxies appear different from many nearby ones. A modern galaxy contains stars of many ages. Its integrated light is a mixture of young blue stars, older red stars, dust, glowing gas, and long histories of star formation. An early galaxy may be dominated by a recent burst. A relatively small number of massive stars can control much of the ultraviolet output. The galaxy's brightness then reflects its youngest members more strongly than its total mass. This is another reason Webb's discoveries cannot be interpreted by simple comparison with mature galaxies. The same amount of starlight does not always represent the same amount of matter. Chemical composition changes the relationship. Metal-poor stars can be hotter and more luminous in ultraviolet wavelengths. Their winds and lifetimes differ from those of stars formed from enriched gas. Their surrounding nebulae may emit more strongly because of the intensity of the radiation passing through them. The term metal-poor can be misleading outside astronomy. Astronomers call every element heavier than helium a metal. Oxygen is a metal in this language, so are carbon, nitrogen, and silicon. A metal-poor galaxy is not empty of complex material. It simply contains a smaller fraction of heavy elements than later systems like the Milky Way. At cosmic dawn, that fraction may rise quickly. A galaxy can begin with nearly pristine gas, experience several bursts of star formation, and become chemically altered within a relatively short time. New material from intergalactic space may then flow in and dilute the enriched gas. A merger may combine systems with different histories. Chemical evolution is not a steady climb. It is a mixture of production, loss, inflow, and recycling. Webb spectra allow astronomers to begin tracing that mixture. One question concerns how rapidly the first galaxies became enriched. If heavy elements appear earlier and in greater amounts than expected, the first stars may have formed sooner, or star formation may have proceeded more efficiently. Massive stars may have dominated the earliest populations. Galaxies may also have retained more supernova material than some models predicted. Another question concerns what is missing. The first completely metal-free stars have not yet been identified directly. Their signatures may be difficult to isolate because they were short-lived, rare, or surrounded by later generations whose light dominates the observation. A galaxy containing only a small fraction of primordial stars may already appear chemically enriched as a whole. Researchers search for unusual spectral combinations that could indicate extremely low metallicity or very hot, metal-free stellar populations. These signals are delicate and can overlap with those produced by black holes or unusual gas conditions. A secure detection will require more than one suggestive feature. It will require a pattern that survives detailed comparison with alternative explanations. Webb may eventually find galaxies caught close to the transition between the first and second generations of stars. Such a system would not be a pristine relic untouched since the Big Bang. It would be an active place where enrichment was beginning, where some clouds remained nearly primordial, while others already contained atoms forged by short-lived stars. That transition may have occurred unevenly across the universe. Dense regions formed stars earlier and enriched sooner. More isolated areas may have preserved simple gas for longer. The first metal-free stars may therefore have continued forming in scattered pockets even after chemically enriched galaxies existed elsewhere. Cosmic history overlaps with itself. The first phase does not end everywhere before the next begins. Webb's view of early galaxies reflects this overlap. One galaxy may appear chemically young but structurally developed. Another may contain a growing black hole in a system with little stellar mass. A third may show oxygen while still existing inside a partly neutral intergalactic environment. The labels early and primitive do not always mean the same thing. A galaxy can be early in time and already complex in process. This has altered the emotional scale of cosmic dawn. Before direct observations, the first galaxies were easy to imagine as dim beginnings barely assembled and chemically empty. Webb suggests a more textured era. So systems were compact and unstable, yet they were already producing stars, heavy elements, radiation, winds, and black holes. They were not complete, they were active. There is an ancient human parallel in the way chemical traces are read. For centuries, people studied light by its color and brightness. Later, prisms separated that light into bands crossed by dark and bright lines. Those lines became a kind of elemental script, allowing observers to identify substances in stars that could never be reached. The same method now reads galaxies from the edge of cosmic dawn. An oxygen line arriving in Webb's detector is not merely a measurement of wavelength. It connects laboratory physics on Earth with atoms formed in stars more than 13 billion years ago. The rules are the same. An oxygen ion absorbs and emits light according to the same quantum structure, whether it exists in a nearby nebula or in one of the earliest known galaxies. Distance changes the wavelength during the journey. It does not change the atom. This continuity allows the remote universe to become measurable. The instruments aboard Webb do not need to visit an early galaxy. They need only receive enough photons to reveal the pattern. From that pattern, scientists can reconstruct temperature, motion, composition, and radiation. The reconstruction remains incomplete. A spectrum can contain noise, Some features overlap. Different physical conditions can produce similar results, yet the method becomes stronger as more galaxies are observed. Individual uncertainty gives way to population trends. Astronomers can compare metallicity with stellar mass. They can ask whether brighter galaxies are more enriched, whether compact systems produce harder radiation, and whether black hole hosts follow a different chemical path from galaxies dominated by stars. These relationships will help distinguish unusual objects from typical ones. They may also show how quickly the first galaxy populations diversified. A universe beginning with nearly the same simple ingredients everywhere produced a wide range of environments within a few 100 million years. Gravity gathered matter at different rates. Stars formed with different efficiencies. Explosions retained or expelled different amounts of material. Galaxies merged, accreted gas, and changed their internal structure. Chemical variation became another form of cosmic structure. The first galaxies were not only assembling mass, they were creating difference. Their stars changed the gas from which future stars would form. Their radiation altered nearby hydrogen. Their winds carried elements outward. Their black holes may have heated or removed material from their centers. Each process made later evolution depend on what had already happened. The universe was developing memory. That memory survives in abundance patterns. The ratio of oxygen to hydrogen can reveal how much stellar processing occurred. Nitrogen may trace different stellar pathways and timescales. Carbon and iron offer other clues, though some elements remain difficult to measure at these distances. No single ratio tells the entire story. Together they constrain the kinds of stars that lived before the light left the galaxy. The deeper Webb looks, the closer these measurements approach the beginning of enrichment. There may never be one first galaxy whose chemical history can be followed cleanly from nothing. Formation occurred across many regions. Some systems lit earlier, some later, and many merged into descendants that no longer preserve simple boundaries. The beginning is a population, not an object. Webb is rewriting that part of the story as well. The first galaxies were not waiting for complexity to arrive from elsewhere. They were the places where complexity began to accumulate. Inside their short-lived stars, the simple matter of the early universe was being rearranged into the elements that would later fill planets, oceans, atmospheres, and living cells. The light now reaching Webb carries that early transformation within it. A faint spectral line becomes evidence that the universe had already begun making new kinds of matter. And somewhere inside that distant glow, the periodic table was starting to take shape. As Webb continues to find earlier galaxies, the edge of the observable story moves closer to the time when starlight first appeared. That edge is not a wall. It is a region of increasing uncertainty, where galaxies become fainter, distances become harder to confirm, and the difference between one interpretation and another can depend on only a few photons. The telescope is now working near the boundary between what can be imaged and what can be measured in detail. A camera can reveal that a source exists. A spectrum can begin to reveal what it is. The distinction matters most at the highest redshifts. Some candidates appear in deep images with colors consistent with galaxies from extremely early times. Their light vanishes in shorter wavelength filters and remains visible in longer ones, as expected when neutral hydrogen and cosmic expansion shift the ultraviolet break into the infrared. From those colors, astronomers can estimate a likely distance, but a candidate at the edge of detection may contain only a small amount of light spread across several filters. A slight change in background subtraction can alter the result. A faint foreground object can overlap the same position. Strong emission from a later galaxy can imitate part of the color pattern. The farther the claim reaches, the more valuable spectroscopy becomes. Spectroscopic confirmation is difficult because the sources are so faint. Webb must remain pointed at one region for many hours, gathering photons that arrive slowly. Even then, the resulting spectrum may contain only a weak continuum and a few possible features. Some galaxies show strong emission lines that make confirmation easier. Others offer only the shape of the break itself. A secure redshift is built from consistency. The observed features must align with one another. The source must behave like a galaxy at that distance across all available filters. Nearby alternatives must fail to explain the same data. This careful process means that the record for the earliest confirmed galaxy can change more slowly than the headlines surrounding new candidates. A candidate may briefly appear to lie farther away than every known object. Later analysis may place it closer. Another may remain plausible for months, while astronomers wait for deeper spectroscopy. This is not a flaw in the search. It is the normal movement from possibility to evidence. At cosmic dawn, the categories themselves become less distinct. A faint source may contain a small galaxy, a compact star cluster, an active black hole, or several merging components unresolved by the telescope. Its measured light could be magnified by foreground gravity. The inferred mass and age depend on assumptions about its star's dust and gas. The object is not uncertain because it lacks reality. It is uncertain because many physical histories can produce a similar signal. The way forward is repetition. Astronomers observe the same source with different instruments. They return at longer wavelengths. They compare several models. They search for emission lines that one explanation predicts and another does not. Webb's near-infrared camera identifies the candidates. Its near-infrared spectrograph tests their distances and gas. Its mid-infrared instrument adds information from longer wavelengths, helping separate older stars, dust, and strong emission features. No single instrument carries the entire story. The telescope was built as a system. That system is especially important when astronomers try to estimate how long a galaxy had been forming stars before the light left it. A spectrum records the combined radiation of many stars. Younger populations tend to emit strongly in ultraviolet wavelengths. Older stars contribute differently at longer wavelengths. By fitting models to the full energy distribution, researchers estimate the age and history of the population. These estimates are not precise clocks. A galaxy that formed stars steadily can resemble one that experienced several bursts. Dust can make a young population look older. Emission lines can increase the brightness of certain filters. A black hole can add a smooth continuum that changes the fit. Even so, some early galaxies appear to contain stars that began forming significantly before the moment Webb observes them. If a galaxy is seen 300 million years after the Big Bang and includes a population tens of millions of years old, its first stars must have appeared earlier still. The search for the first galaxies therefore becomes a search through layers of ancestry. The earliest confirmed object is not necessarily the first galaxy that existed. It is the earliest one whose light has survived in a form bright enough to detect and clear enough to interpret. Fainter systems almost certainly existed beyond the present limit. Some may have formed stars briefly and then faded. Some may have merged into brighter galaxies before sending enough light toward us to be recognized individually. The observational frontier is shaped by luminosity as much as by time. This creates a basic asymmetry. Astronomers learn first about the rare galaxies that were easiest to see. They may have formed in dense regions where dark matter halos appeared early. They may have gathered gas efficiently. They may have contained unusually luminous stars or active black holes. The ordinary galaxies of the same era may remain hidden below the detection threshold. To recover that unseen population, researchers use statistics. They measure how the number of observed galaxies changes with brightness. They estimate the shape of the luminosity function and extend it toward fainter values. They compare the results with simulations of halo growth and star formation. This extrapolation influences many conclusions. The total amount of starlight in the early universe depends heavily on how many faint galaxies existed. So does the estimated supply of ionizing photons available for reionization. A small change in the faint end of the population can alter the larger history. Gravitational lensing helps reach lower luminosities. A massive cluster of galaxies bends spacetime around it. Light passing through that curved region can be magnified, allowing Webb to detect background sources that would otherwise be too faint. The effect can act like a natural telescope, placed between Earth and cosmic dawn. It is powerful and imperfect. The amount of magnification depends on the distribution of mass in the foreground cluster. Different models can produce different estimates. A source may be stretched into an arc or split into multiple images. The brightest part of a galaxy may be magnified differently from the rest. Researchers must reconstruct the unlensed object from the distorted view. Even with these complications, lensing reveals a population inaccessible to blank field surveys. Some of the smallest early galaxies known have been found behind foreground clusters. They offer clues about whether common low-mass systems could have supplied much of the radiation that reionized the universe. They also show how star formation behaved in halos far smaller than those hosting the bright galaxies that dominate the deepest images. The two approaches complement each other. Blank fields provide more straightforward measurements over larger volumes. Lensing fields reach farther down the brightness scale. Wide surveys find rare luminous galaxies. Deep surveys uncover the common faint ones. The first complete picture of cosmic dawn will need all of them. It will also need observatories beyond Webb. Webb is sensitive to infrared light from stars and ionized gas. It cannot map the full distribution of neutral hydrogen that surrounded the first galaxies. Radio observatories are being developed to detect the redshifted 21 centimeter signal from that gas. If those maps become sufficiently detailed, astronomers may be able to place Webb's galaxies inside the ionized bubbles they helped create. A bright galaxy could be seen at the center of a large, cleared region. A group of fainter systems might explain an irregular bubble. Some galaxies may appear in areas that remained neutral longer than average. This would connect the sources to the medium they changed. Other telescopes will add different wavelengths. X-ray observatories can search for growing black holes. Large, ground-based telescopes can obtain higher resolution spectra for selected sources, especially as instruments improve. Millimeter observatories can detect cool gas, dust and emission from elements such as carbon and oxygen in galaxies beyond Webb's strongest range. No observatory sees the first galaxies completely. Their history is distributed across the spectrum. This wider network of observations will test some of Webb's most important suggestions. Were bright galaxies truly common at very early times? Did star formation proceed in intense bursts? Were black holes already widespread in compact systems? How quickly did heavy elements and dust accumulate? Which galaxies allowed ionizing radiation to escape? The answers will not emerge from one famous object. They will come from patterns repeated across many fields. This is the stage the science is now entering. The first Webb images produced surprise because they revealed individual galaxies that seemed brighter or earlier than expected. The next phase is slower. Samples must grow. Selection effects must be measured. Different surveys must be placed on the same scale. Spectra must be compared using consistent methods. Uncertain objects must be separated from secure ones. The work becomes less dramatic and more powerful. A single record holder can move the boundary of observation. A population can change the model. There is also a limit imposed by the universe itself. Before the first stars formed, there were no galaxies producing starlight for Webb to detect. Moving farther back eventually leads into the Dark Ages, where ordinary matter existed without luminous structure. Webb may approach that transition, but it cannot see through it using galaxy light. The first sources were likely small, brief, and faint. Their radiation may be too weak to isolate individually across such distance. Astronomers may instead detect their collective effects. The chemical patterns in slightly later galaxies can preserve traces of the first stellar generation. The timing of reionization constrains when ionizing sources became common. The 21 centimeter signal may reveal when the first radiation began heating and ionizing hydrogen. The earliest light may be known partly through what it changed. This is a recurring feature of astronomy. Some objects are studied directly, others are reconstructed from consequences. Dark matter is mapped through gravity. Black holes are measured through the motion and radiation of surrounding material. The first stars may be inferred from the elements temperatures, and ionization states they left behind. Webb brings that indirect history closer to direct observation than any earlier telescope. It can see galaxies from a time when the first stellar generations may still have been influencing the gas around them. It can search their spectra for unusual chemical and radiation signatures. It can compare systems at slightly different ages and watch, in a statistical sense, how the population changes. The difference between two distant galaxies may represent only several tens of millions of years. In the early universe, that interval can contain major transformation. A small halo can begin forming stars. A massive star can live and die. Heavy elements can enter the gas. A black hole can grow. An ionized bubble can expand. The pace of physical change was rapid, even though the light reaches us as a still image. To place these objects in sequence, astronomers use redshift as a kind of layered time coordinate. Higher redshift generally corresponds to earlier observation. But the sequence is not a film of one galaxy evolving. Each point belongs to a different object in a different region. The history must be assembled from many places. One galaxy shows an early chemical stage. Another shows rapid black hole growth. Another appears inside a large ionized environment. Another is bright enough to reveal its structure. Together, they form a composite account. That account will always contain gaps. The first galaxies were numerous, distant, and varied. Most will never be observed individually. Their photons spread across expanding space, often becoming too faint for any instrument now imagined. Science does not require every object to be seen. It requires enough evidence to constrain what the hidden population could have been. Webb has already narrowed that range. The young universe could produce luminous galaxies earlier than many models predicted. Some systems enriched their gas quickly. Compact black holes were active, ionized regions were growing. The galaxy population may have been more burst-like and diverse than a smooth average suggested. The remaining uncertainty is no longer an empty space. It has shape. Researchers know which measurements are missing. They know which models disagree. They know which new observations would distinguish one explanation from another. That is one of Webb's quieter achievements. It has turned cosmic dawn from a distant chapter with only broad outlines into a field of specific, testable problems. The telescope has not reached the first light yet, but it has made the path toward it visible. The first galaxies are still far beyond the reach of any journey. No base spacecraft can cross the distance between here and cosmic dawn. No future telescope will watch one of these systems age in real time. Their stars have changed, merged, faded, or disappeared during the billions of years their light has spent traveling toward us. What remains is a record carried by photons. Those photons do not arrive with labels. They do not identify the mass of a galaxy, the age of its stars, the size of its black hole, or the amount of hydrogen surrounding it. They bring brightness, wavelength, direction, and time, encoded through distance. Everything else must be recovered through measurement and comparison. This is why the story Webb is rewriting will never become a single dramatic correction. It will become a more detailed history. The earliest galaxies once occupied a narrow role in cosmology. They were expected to be small structures, growing gradually inside dark matter halos, building stars, enriching gas, and joining into larger systems. Webb has preserved that broad foundation, while revealing how much variation had been hidden inside it. Some galaxies became luminous very early. Some formed stars in concentrated episodes. Some already contained oxygen and other products of previous stellar generations. Some hosted growing black holes inside compact stellar systems. Some may have helped carve large ionized regions into the neutral hydrogen around them. None of these findings requires the young universe to ignore physical law. They require the models to account for a wider range of physical behavior. Gas did not enter every halo at the same rate. Feedback did not affect every cloud uniformly. Stars did not form with identical histories. Black holes did not wait for galaxies to become mature before beginning to grow. The first several 100 million years were not a simple prelude. They were an active stage of cosmic construction. Webb is able to observe that stage because the universe has stretched its light into infrared wavelengths. Radiation that began as ultraviolet starlight arrives after a journey through expanding space, weakened but preserved well enough for a cold telescope to receive it. The mirror does not gather the entire past. It gathers what survived. Some photons were absorbed by dust, some scattered through hydrogen, some never traveled in Earth's direction. Some sources were too faint to leave a detectable trace. The galaxies in Webb's images are therefore a selected population shaped by brightness, geometry, and chance. They are not every early galaxy. They are the ones whose light crossed the distance successfully and entered the small region of sky being observed. This limitation is part of the evidence. Astronomers measure what can be seen, then calculate what must remain below the threshold. They compare deep fields with wider surveys. They use gravitational lensing to find weaker systems and spectroscopy to test the brightest candidates. The emerging picture is built from many incomplete views. That may be the most accurate way to understand cosmic dawn. It was never one event. The first stars did not ignite everywhere at once. The first galaxies did not all pass through the same stages together. Reionization did not sweep across space as a smooth front. Different regions followed different clocks. A dense knot in the cosmic web could begin forming stars, while another region remained dark. One galaxy might enrich its gas rapidly, while another continued drawing in material close to its original composition. A black hole could grow in one compact system, while a neighboring halo contained only scattered star clusters. The universe moved forward unevenly. Webb is now resolving some of that unevenness into individual objects. A faint red source is no longer only a prediction inside a simulation. It can be assigned a redshift. Its spectrum can be examined. Its oxygen emission can be measured. Its size can be estimated. Its possible black hole can be compared with the stars around it. Each result adds another constraint to the history. Some constraints will later be revised. A galaxy may prove closer than first estimated. A stellar mass may fall when emission lines are modeled more accurately. A suspected black hole may turn out to be a dense star-forming region. Another object may become more significant after deeper observations reveal a secure spectral feature. Revision does not erase the earlier work. It is how the field moves from a first impression toward a durable account. The earliest Webb observations created a sense that the young universe had appeared too developed too soon. Several years of analysis have made that question more precise. Some initial tensions weakened, others remained. New categories of objects appeared that were not central to earlier expectations. The result is more interesting than either complete agreement or complete collapse. Galaxy formation models remain useful. They now have more to explain. They must reproduce not only average growth, but brief luminous phases. They must connect stars with black holes, enrichment with inflow, feedback with escape, and galaxy populations with the progress of reionization. A model that succeeds will need to describe a universe that could be both young and busy. That work will continue beyond Webb's current surveys. More observing time will enlarge the samples. Better spectroscopy will test uncertain distances. Longer wavelength measurements will improve estimates of stellar age and dust. Radio maps may eventually reveal the neutral hydrogen around the galaxy's Webb seas. Future instruments will not replace Webb's view. They will place it inside a broader one. The first galaxies will become points within maps of ionized bubbles, dark matter structure, gas temperature, and chemical development. Individual discoveries will join into an environmental history. Even then, the beginning will remain partly hidden. The very first stars may be too faint and too brief to isolate directly. The smallest galaxies may never rise above the background. Some of the earliest black hole seeds may be known only through the later objects they produced. Cosmology often advances through traces. A structure leaves gravity behind. A star leaves elements. A black hole leaves motion and heat. An early galaxy leaves light stretched across most of cosmic time. Webb receives those traces in a place far from Earth, shielded from sunlight and cooled for infrared observation. Its mirror faces outward, while the planet that built it moves around the Sun, and the Sun moves through the Milky Way. The geometry of the observation is temporary. The light is ancient. For several hours, the telescope holds its pointing while photons gather in a detector. On Earth, those measurements become files, calibrated images, spectra, plots, and arguments. Months may pass before a result becomes clear enough to publish. The universe does not hurry during that process. The galaxy has already sent what it could send. The rest belongs to interpretation. There is something fitting in the distance between those two acts. A young galaxy forms stars, lights gas, perhaps feeds a black hole, and releases radiation into space. More than 13 billion years later, a species on a small planet builds an instrument capable of separating that radiation into wavelengths and asking what happened. The connection is narrow. Only light passes between them. Yet, light is enough to reveal that the early universe was already layered with structure, chemistry, motion, and change. Webb has shown that cosmic dawn was not merely the time before familiar galaxies. It was the period when the relationships defining later galaxies were beginning to take form. Stars were changing gas. Gas was feeding black holes. Radiation was changing intergalactic space. Gravity was gathering separate systems into larger ones. Elements were accumulating inside environments that would eventually become the raw material of planets. The Milky Way belongs to the far continuation of that process. Its oldest stars preserve traces of early enrichment. Its central black hole belongs to a population whose roots may reach back toward the compact sources Webb now studies. Its spiral structure emerged after countless mergers, inflows, stellar deaths, and periods of rebuilding. The first galaxies are not separate from the present universe. They are its unfinished beginning. The atoms around you did not come from one of the specific galaxies visible in a Webb deep field. Their exact path cannot be traced that way. But the processes seen there are part of the same history that eventually produced the chemical universe around us. Hydrogen entered stars. Stars made heavier elements. Galaxies retained, lost, and exchanged them. New generations formed. The pattern continued. Webb looks backward to the stage when that pattern had only recently begun. Its discoveries will keep changing as the observations improve. Record holders will be replaced, mass estimates will be adjusted. Some mysteries will become ordinary once the correct physical assumptions are included. Other questions may remain for decades. That is not an unfinished failure. It is the natural shape of a field approaching a frontier where the evidence is faint and the consequences are large. For now, the first galaxies remain small marks in infrared images. Their forms are blurred by distance. Their persistent spectra, their present state is unreachable. But the light they released has arrived, and within it, the young universe is no longer silent. Across the dark between galaxies, the first light is still finding its way home.